Alright class, what's up today? First things first, got an eraser, so erasing will be a little bit quicker. I also got some new colored pens, so those will hopefully help. Today we're going to be talking about some kind of like new types of functions. We've looked at like integral power rule, we've looked at addition and subtraction within integrals, we've looked at bounded and unbounded integrals, so we're going to start looking at integration methods and techniques. And in this video we're going to talk about a couple of functions, mainly like rational logarithmic functions, maybe exponential functions, I guess. Probably won't get to that today, actually. But we're going to talk about these certain types of functions that may have special integration techniques or things you have to watch out for, really, when integrating. So I'm going to define a function. Let's say f of x is equal to integral of 1 over x dx, right? And this is going to be an unbounded integral. So this integral is just going to, or this function is simply just going to be the integral of another function, the antiderivative of another function. But this is a tricky function. 1 over x is. I'll use red for this one because this is what we don't want to do. We don't want to say this is equal to the integral of x to the negative 1 dx. And you might think, oh, you can do this. You can represent 1 over x as x to the negative first power, and then just use our power rule, right? Okay, so now we add 1 to the power, and then divide by the new power. Okay, that doesn't work. We get x to the 0 over 0, which would just be 1 over 0, and that doesn't make sense, right? So what happens? The power rule works for every other polynomial function, but this one, 1 over x, is a special one. So 1 over x, if you didn't already know, is what's called a rational function. It's going to be a function which you can write as a fraction. Usually you're going to have some, well, almost always you're going to have some variable in the denominator, and usually that's going to lead to some sort of like vertical asymptote sort of deal, right? And so now what we tried to do is we tried to take the derivative of a function that's not continuous on its entire interval, right? 1 over x has that discontinuity due to a vertical asymptote at x equals 0, right? And we try to integrate that there. However, and mathematicians have figured out over many years, and I won't go into too much detail, I'll just kind of tell you how you actually evaluate this integral, because the integral of 1 over x dx does actually have, you can compute this integral, and it does exist. It's not undefined, right? And this is an important identity. I'm just going to kind of give it to you broadly. It's equal to natural log of x plus c, right? And this natural log is the argument, or this x is the argument of natural log, right? Natural log, again, is the logarithm with base e, Euler's constant, about 2.723 or something like that. Perfect number in mathematics. It's the number in which I don't know if we had a video over this, but the derivative of e to the x is e to the x. I think we had a video on this. Fun fact, the integral of e to the x dx is also just equal to e to the x, so, and I guess plus c, but yeah, Euler's constant is a very special number in mathematics, and it just happens to be that the integral of this rational function computes to be the natural logarithm of x, right? So that's a special identity in mathematics. A lot of times, and in future videos, I'll use this one as an example a lot, because it works well with the content we're going to see in the future. Very often we'll see rational functions in calculus, and a lot of times you can simplify it to some sort of natural logarithm, right? And let's think about why this works. I'm going to kind of attempt to draw out f of x equals 1 over x. It'll look like this, right? It's going to look like this. This is the positive x-axis. This is, let's say, f of x, right? And now the natural logarithm function is going to look something like this, with the natural log being equal to 0 at x equals 1, right? Because if you were, if we're plugging in natural log of 1, that's equal to 0. Because, and if you've never read a natural logarithm before, the way you would read this is simply, okay, e to the what power is equal to 1? Well, e to the 0th power is equal to 1. So the natural log of 1 is simply 0, right? So the natural log graph is going to have an x-intercept at x equals 1. And this up here, and I'll use a different color for this, is a vertical asymptote here at x equals 0. And this is also a vertical asymptote here at y equals 0 on the rational function. There's also one here on the horizontal axis for the rational function, but not for the logarithmic function. The logarithmic function does, in fact, grow forever. It will just continuously grow forever. The natural log is continuous on its domain, on its entire domain. However, the rational function has this discontinuity to this vertical asymptote. We have function on both sides, right? But it's really, really interesting to think about how we get from here to here. And it has to do with actually the derivative and the antiderivative. Now, I'll switch my color here. If the integral of 1 over x dx is natural log of x, then what's the derivative of natural log of x? Well, if derivatives are just the backwards antiderivatives, this I claim is 1 over x. And so we know that the integral of 1 over x must be some function natural log of x, because the slope of the natural logarithm function can be represented by the rational function 1 over x, right? And as down here, kind of towards x equals 0, you're going to have a high slope, right? And that slope is actually going to increase, as you approach y equals 0, x equals negative infinity and all that, right? But then as you keep going and going, your slope is decreasing and decreasing and decreasing. But your slope never hits 0, so natural log actually does continue to grow forever, right? The rational function approaches this 0 and stops kind of decreasing meaningfully after a while, right? So yeah, I thought that was cool. We kind of have this identity of the integral of the rational function 1 over x being natural log of x. And it seems to be so weird because we can take the integral of 1 over x squared dx like perfectly normally with just our power rule, because this is equal to the integral of x to the negative 2 dx, which is equal to, okay, x to the negative 1 over negative 1, which is just equal to negative 1 over x, right? So we can take the integral of any other polynomial function, except for that one in which your exponents can be negative 1, or you have that singular x in the denominator, right? And so when I touched on this earlier, we'll talk a little bit more about Euler's constant, because I think it's, like, even if you've heard of it before, it's a interesting refresher. Now, I believe Euler's constant actually comes from a limit. It's going to be a limit as, like, x approaches infinity of, I believe, 1 plus 1 over x to the x power, right? And so this is actually equal to e, right? It's interesting, but it turns out that limit has very, very, very special properties in mathematics and is very applicable to our world, given d dx of the exponential function e to the x is just equal to e to the x, right? And now, derivative of e to the x, here, integral of e to the x dx is just e to the x, and then plus c, of course, right? Because we never forget that constant of integration. And then, just to kind of conclude it off, second fundamental theorem of calculus, derivative of the integral of e to the x, just e to the x, right? So, Euler's constant, really, it's my favorite number. I'm not going to lie there. Euler's constant is definitely my favorite number. So, thank you for joining me for this shorter video on kind of this trick we need to remember with the natural logarithm function. Next video is going to be a lot longer. We're going to see kind of everything we've learned up in calculus to this point so far, and an integration technique of substitution that's going to help us solve integrals that previously we wouldn't have been able to before. So thank you very much for joining me today, class. I'll see you in the next video.